Hi, this is the first in a series of instructional videos on equipment that you might find in a typical physics lab or electrical engineering lab. We're first going to be taking a look at the functionality of the Fluke87V digital multimeter, or DMM. So all of the connections made to this are through banana jacks and the associated connector, the banana connector. Here is a banana connector to banana connector cable, or two of them. We also have banana connector to alligator clips. These are useful for connecting to individual wires of components with these little grabby alligator guys. We also have, I make these are banana connectors to solid 22 gauge wire so that they're easily inserted into a breadboard, so I can just leave this wire in the breadboard and make measurements. We also have this connector that has banana connectors that are spaced 0.75 inches apart, so they easily fit into the terminals of the DMM and can be made we can make connections to B and C cables. But what we're going to start off using are the included probes, which have insulated banana connectors to probes. It's important to use the Fluke probes that come with the DMM because they are Cat 3 rated to 1000 volts. Still, when you are making connections to high voltages, OSHA defines high voltages 42 volts and above, but voltages below that can still be dangerous. Don't touch the metal while also making contact to any sort of high voltage. So let's just go ahead and plug these in, the red terminal to the rightmost terminal and the black cable to the COM or common terminal, and make some measurements with these. Let's take a tour around the DMM's multi-selector. So first we come to AC volts. This measures voltage in RMS AC voltage, and first we'll just measure the voltages on a typical North American outlet. Now, the outlet has three prongs. The mouth part, or the bottom kind of round connector, is earth ground, and the kind of dilated eye of this face, the larger spade connector, is also connected to is the neutral and is also connected to ground at the breaker box. We can talk more about that later. The hot terminal is the undilated eye of this face, and that is where we should measure 120 volts RMS. So I'm going to carefully plug this in to there, between the neutral and the hot terminals, and we should get around, may not be making good connection. There we are, around 120 volts RMS. Now I can also measure between the hot and the ground, and that is also around 120 volts RMS. Now, seeing as that these are connected, the neutral and the ground are connected at the breaker box, I shouldn't measure any potential difference, but I do measure some around 300 millivolts RMS voltage, and I leave it to you to figure out why this is. Remember, this forms a loop with the terminals at the junction box, and this is AC voltage, so that may give you some clue. Okay, so that's AC volts. Let's move to the 10 o'clock position on the multi-selector to DC voltage, and to measure, to make DC measurements. I will demonstrate that using a battery. I'll connect the black probe to the negative terminal and the red probe to the positive terminal, and I get 8.89 volts. Now if I swap those terminals, I get negative 8.89 volts. It's all about, whether you get positive or negative is all about where you define your zero voltage point, or your ground voltage. So that's that. Interestingly, inside of a 9-volt battery. If I can get this open. There are 6 quadruple A batteries. So we can also measure these. These should be at 1.5 volts each. I know that the little nubbin on each one of these is the negative terminal. So that one is 1.34 volts. So that's kind of interesting. Quadruple A batteries. Maybe you've never heard of that before. So let's continue on our journey through the multi-selector. We have millivolts DC, so this just gives us an extra digit. The one useful thing this is useful for is measuring temperature. The Fluke87V includes a Type K thermocouple, and thermocouples are devices that are just 2 dissimilar metals in a Type K thermocouple. These metals are chromel and alumel, and they form a junction here at the very tip, the temperature sensitive point. And if there's a temperature gradient on the thermocouple, it exhibits the thermoelectric effect and generates a small voltage that can be measured and used to measure the temperature. So I press the yellow button to put it in temperature mode, and we can see that the temperature in this room is 24.6 degrees Celsius. All right, so that's useful. Let's go to the 12 o'clock position, and the primary measurement mode here is measuring resistances. Resistors come in all shapes and sizes. Everything to this very tiny surface mount resistor here, to carbon film resistors, which is this tan resistor. This blue resistor is a metal film resistor. This is a higher power resistor. I'm actually not sure what this is. It may be carbon film or wire wound, perhaps even thick film, all the way up to this large resistor. And the difference between the smaller resistors and the very large resistors is how much power they can dissipate. So I know that the carbon film resistor and the metal film resistor can dissipate 1/4 watt of power. This one can dissipate 10 watts of power, and this one can dissipate 250 watts of power. So the simplest model of a resistor is, or the simplest resistor that we can make is a wire wound resistor. These are just coils of copper that have different lengths and cross-sectional areas. If you look at this or remember this equation, the resistance is equal to the resistivity times the length divided by the cross-sectional area of that conductor. The resistivity is a property of the material, and so hopefully we can see that here. First off, we've got a 10 meters of gauge 22 wire. And we can measure the resistance of that, and that is around 0.7 ohms. I also have 20 meters of the same wire, the same cross-sectional area, so it should be about double that, or 1.4 ohms. It's a little bit low, but you get the point. I also have 10 meters of gauge 28 wire, which has a smaller cross-sectional area, so should have a higher resistance. That's about 2.4 ohms. Then I have 20 meters of this, so this should be around 4.8 ohms. Again, a little bit lower for some reason. And these are all copper, so they should scale appropriately, but they all have the same resistivity. But I also have some nickel-silver wire, which has a different resistivity. It's 10 meters, number 22, gauge 22 wire, and it is 9 ohms, so it has a higher resistivity. Now let's just go through and measure each one of these resistors. This small surface mount resistor I know to be 5.1 ohms. So that's, I'm sorry, 5.1 kilo ohms, which is what is indicated on the display. I know this to be a 1 kilo ohm resistor. Now, here's a measurement note. When measuring resistors, you can make contact with your body on one lead of the resistor, but usually I try not to make contact with the other lead. So this is 0.98 kilo ohms. And the reason for that is that depending on how moist you are, you can actually have a resistance. So here I'm just touching these two terminals. I guess I'm pretty sweaty, so I've got about 0.9 mega ohms of resistance. If I touch closer, 0.7 mega ohms, and I don't want to have my body's resistance foul up the measurement. So I'll do the same thing here on this metal film. I know this to be a 1% 10 kilo ohm resistor, and that's very close to 10 kilo ohms. This is a 10 ohm resistor, this bigger, larger one. And that is about right. That's almost spot on. And then this large one is 120 ohms. And we get something very close to that. Now, resistors can also sense the environment. Here I have a CDS cell, or cadmium sulfide resistor, which is a light-dependent resistor. And why don't I switch to the alligator clips to make this a little bit easier to make connections to the leads of the sensor, the resistive sensor. There's that one. Here's this one. You can see that nominally it's at 3.8 kilo ohms, and when I cover it, the resistance gets higher and is 35 kilo ohms. So you can make a little light sensor out of that. I also have a pressure sensor here. Make a connection there and see that it's over level right now. It's very high resistance, but when I press on it, it goes down to even 0.5 kilo ohms, or around 500 ohms. So this has a very high dynamic range in terms of resistance. I also have a piece of conductive rubber. I can make connections to either end. Nominally about 2.5 kilo ohms, but when I stretch it, the resistance changes. So you can see how you can make sensors out of various resistive materials. So another resistor that is very useful in the lab is called a potentiometer. The schematic symbol for a potentiometer is shown here. We have three terminals. One is just a fixed resistor, or between two terminals is just a fixed resistor. And the other terminal is the wiper. So the resistance between these two terminals or these two terminals will change depending on where this wiper's position is in either its rotary or linear scale. So I will do the same thing. Let's connect to the end two terminals first. And we see that we've got 9.5 kilo ohms. And as I rotate the resistor, or the potentiometer, the knob of the potentiometer, nothing happens. But when I connect to the middle pin, I'm fully clockwise right now. It's at 9.5 kilo ohms. And I can turn it counterclockwise, and it will go all the way down to close to 0 ohms. I can do the same thing with the other two terminals. And here we're fully counterclockwise, and it's at 10 kilo ohms. And as I turn it clockwise, I go down to close to 0 ohms. Potentiometers come in many shapes and sizes. This is a linear potentiometer out of a piece of audio equipment, and I like using these breadboard potentiometers because they are good for prototyping. Another function at the 12 o'clock position of the multi-selector is the continuity function. So this function just gives you an audible tone when the two tips are connected. So this is good for checking continuity in different circuits, making 2 points in a circuit are connected. And to demonstrate this, I have a switch, and this switch This switch is a single pole, single throw switch, so it only has two connectors. This is the schematic symbol for this, so when it's depressed, this becomes a wire, and when it is not depressed, it is open. It's an open circuit. So I'll make connections here, and I can see when I press it, it makes a connection. There are many other types of switches. This is a toggle switch and actually has 6 terminals. This is a double pole, double throw switch, and this is actually 2 independent single pole double throw switches. So that means that there is one common connection and then 2 connections that it can be made to. So I know that the common connection is the middle pin, and that one is connected right now, but when I switch it, it is off. So now, when I make this other connection on the other side, whoop, that is not connected, and now it's connected. So you can see how you can ferry signals around using these different types of switches. Also on this, on the 12 o'clock position, is a capacitance measurement. To get into capacitance measurement mode, I press the yellow button, and here I've got a 22 microfarad capacitor. Connect that, and it is indeed close to 22 microfarads at 23.4 microfarads. Okay, continuing on. We have a diode measurement function, and diodes are interesting in that they are nonlinear devices. If we plot the current as a function of the current through the diode as a function of the voltage across the diode, we get an exponential, or something closely approximating an exponential curve. What the diode measurement function does is it is a constant current source at 1 milliamp of current. So it tells us the voltage drop across that diode at 1 milliamp. So let's just test this. It's a nice 1 milliamp current source. So this is a silicon diode. The band on the diode is always the cathode, so we will connect it in that manner. And so we see on the silicon diode we have a 0.6 volt DC drop. This is a silicon Schottky diode. It actually has a lower voltage drop at 1 milliamp, and so that is 0.2 volts. I also have a germanium diode here. These were used in old-timey radio sets. That is around 0.6 volts. Actually, it should be a bit smaller than that, but 0.5, it's a little bit lower than the silicon diode. And then finally, I have a light-emitting diode. Connect that to the cathode, this to the anode, and that is 1.67 volts at 1 milliamp. And you can see that it's just barely lighting there. I would like to connect this DMM. I'll put this back into DC voltage mode and connect it directly to a DC power supply. I connect just to the negative terminal and the positive terminal of the power supply. This green terminal I usually leave disconnected. It is a grounding terminal, but we usually use some other place in the circuit to be our ground. Specifically on the oscilloscope, all of the outer jackets of these B and C connectors are connected to earth ground, and to avoid any ground loops and any noise in our system, we just use the positive and negative terminals of this power supply. Now the positive and negative terminals act like a variable battery, and we can see that this one goes from 0 to 25 volts DC, and as I increase the voltage, I see that I can measure voltage out to 100 microvolts, and the power supply indicates just down to 10 millivolts. So we get much better precision with this DMM. So I can continue on. This is a 10-turn potentiometer on the power supply, so I get pretty good resolution. And you can see this goes all the way up to 27.9 volts, and we get one extra digit of resolution on the multimeter. So we'll see how we can actually plot this on the oscilloscope in the next video. One often confusing measurement is the measurement of current using the DMM. So to illustrate that, I'm going to measure the current flowing through this large resistor using the DMM. And so to do that, this is DC current, so I'll turn the multi-selector to the 2 o'clock position. And right now we see that we're measuring AC amps. To measure DC amps, we press the little yellow button here and we switch to DC mode. So we always measure current in series, and we are using the other terminals on this DMM. Now we need to be very careful in making connections to these terminals because of the fuses that are involved. So we always want to limit the current flowing through the system using a resistor or some other device. We never want to connect these directly to a power supply because it will blow the fuses in here, and these fuses are actually quite expensive. They're about $5 or $6 each, and we can see that between the milliamp or microamp terminal and the common terminal, it is fused with a 400 milliamps fuse. So if we run more than 400 milliamps through there, we will blow that fuse. Similarly, with the large or the regular A and common terminal, that is 10 amps max. So if you put more than 10 amps through here, it will blow the fuse. Fortunately, these power supplies and most power supplies in the lab only go up to 1 amp or a couple of amps, so it would be impossible to blow that fuse with most of the power supplies in the lab. So since we measure these in series, I'm first going to connect using the banana-to-banana cable the positive terminal of our variable battery to the large A terminal, and the common terminal will go to one end of the resistor using the alligator clip, and the other terminal of the resistor will go to the return or the negative terminal of the battery. So the current flows out of the positive terminal into the amps range of this DMM, out of the common terminal into the resistor, and then it returns to the negative terminal. So we have a complete circuit here. So I'll increase the voltage across the terminals of this battery, or I'm sorry, across the terminals of the battery, but also across the terminals of the resistor. And we can see that the current flowing through the resistor is around 100 milliamps. It increases about to 100 milliamps. I know this is 120 ohms, so according to Ohm's law, V equals IR, the voltage, 12 volts, divided by the resistance, 120 ohms, is about 100 milliamps.